February 3, 1943. Telefunken Research Laboratories, Berlin Tempelhof, Germany. Professor Leo Brandt's hands trembled slightly as he lifted the copper cylinder from its protective case, examining what would later be called the most significant intelligence failure in Nazi radar development. The device, no larger than a coffee mug and weighing barely 3 kilograms, contradicted everything German physicists had calculated about microwave radar technology. This cannot be generating such power at 3 gigahertz. Our mathematics proved such power levels impossible at these wavelengths. 24 hours earlier, Luftwaffe night fighters had shot down a Royal Air Force Sterling bomber near Rotterdam. The aircraft, part of Pathfinder Force, carried equipment so secret that it included self-destruct charges designed to obliterate the technology before enemy capture. Those charges had failed. German recovery teams found the radar system largely intact, its copper magnetron still warm from operation. What German scientists discovered when they examined that device would expose a technological gap so profound that it would force German leadership to confront an uncomfortable reality. The Allies were not just ahead, but operating in an entirely different realm of physics. The capture of that single component would reveal that Germany was not fighting the same technological war. They were years behind in understanding how to harness the power of centimetric wavelengths. The story of this technological chasm began not with defeat, but with a decision made at the height of German military triumph. Following the spectacular fall of France in June 1940, with Britain seemingly isolated and vulnerable, Adolf Hitler issued a decree that would handicap German science for the duration of the war. The Führer decreed that no scientific research project could receive priority funding unless it promised definitive military results by 1942, approximately 2 years from the directive. This single administrative decision, born from overconfidence in swift victory, would cost Germany its technological edge in the most crucial electronic warfare development of the conflict. The decree effectively killed long-term radar research in Germany, just as British scientists were making breakthroughs that would change warfare forever. Dr. Wilhelm Runge, head of radar development at Telefunken, had seen the mathematical limitations clearly. German scientists understood the theoretical principles of cavity magnetrons. Hans Hollmann had even filed a patent for a multi-cavity design on November 27, 1935, years before the British work. His United States patent 2,123,728 was granted on July 12, 1938, describing a magnetron with multiple segments connected by straps to increase efficiency. Soviet physicists Nikolai Alexeyev and Dmitry Malyarov had published research on cavity magnetrons in Leningrad in 1936, work that German scientists had reviewed. The theory was not secret. International physics journals had carried articles on magnetron development throughout the 1,930 seconds. What eluded German engineers was the practical implementation at high power levels and stable frequencies. German calculations, performed by some of the Reich's most capable physicists, suggested that magnetrons operating above 1 gigahertz would be fundamentally unstable, prone to frequency drift that would make them useless for precision radar applications. Experimental prototypes built in German laboratories had validated these concerns. The devices either failed to oscillate at the desired frequencies or produced such low power outputs, perhaps 30 to 50 watts, that they seemed impractical for military applications. Based on these calculations and experimental results, reinforced by the urgency of wartime production demands, German radar development committed entirely to lower frequencies where established technology functioned reliably. By 1942, German radar systems operated primarily between 90 and 600 MHz, using klystron tubes and specialized triodes that German industry could manufacture consistently. These systems worked admirably for their intended purpose. The technology was mature, understood, and producible at scale, but they required antenna arrays measured in meters and provided resolution measured in hundreds of meters. For early warning and general aircraft tracking, these limitations were acceptable. For precision applications, they represented fundamental constraints that German engineers believed were unavoidable, given the laws of physics as they understood them. The Würzburg radar represented the pinnacle of German tracking radar technology. Operating at 53 centimeters wavelength with a 3-meter parabolic dish antenna, manufactured by the Zeppelin Company, it could track aircraft with acceptable accuracy at 40 kilometers range. The system used a conical scanning technique introduced in the Würzburg D model in 1941, employing an offset receiver feed called a quirl that rotated at 25 Hz. This provided angular resolution of approximately 0.2 degrees in azimuth and 0.3 degrees in elevation, sufficient for directing night fighters toward bomber formations, but not precise enough for direct gun laying without optical assistance. The larger Würzburg Riese, the giant Würzburg, represented Germany's most advanced operational radar. Based on the same receiver circuitry and displays as the D model, the Riese featured a much larger 7.4-meter parabolic antenna and a more powerful transmitter. This extended maximum range to 70 kilometers against aircraft targets, with the improved angular accuracy needed for direct gun laying. The system was too large for mobile deployment and was typically mounted on railway flat cars as the Würzburg Riese E variant. Approximately 1,500 of these systems were produced during the war, forming the backbone of German air defense. Freya early warning radars, operating at wavelengths between 2.5 and 2.3 meters, provided long-range detection capabilities that complemented Würzburg's precision tracking. With peak power output of 15 to 20 kilowatts and pulse repetition frequency of 500 Hz, Freya could detect approaching bomber formations at ranges up to 160 kilometers. The system could not accurately determine altitude, but it provided early warning that allowed Würzburg stations to be alerted and night fighters to be scrambled. Together, these systems formed the Himmelbett Line defense network that had inflicted substantial losses on RAF Bomber Command throughout 1941 and 1942. German confidence in their radar superiority was not without foundation. The Wehrmacht had deployed radar earlier and more extensively than any military except the British. German radar-directed anti-aircraft fire was more effective than anything the Allies could match in 1941 and early 1942. The night fighter defense system, using ground-controlled interception guided by Würzburg radar, had achieved remarkable success rates. German engineers looked at their radar network with justified pride. They had built effective, reliable systems using sound engineering principles. What they did not know was that British scientists had transcended the limitations German theory declared absolute. That confidence began eroding in late 1942. Bomber command losses, which had been climbing steadily as German night fighter tactics improved and radar coverage expanded, suddenly began diverging in ways that troubled German air defense analysts. British bombers seemed able to navigate with precision through heavy cloud cover and darkness. They found targets in conditions that should have made navigation impossible without visual reference to ground features. Pathfinder aircraft marked objectives with accuracy that suggested they possessed navigational aids superior to anything Germany had fielded. Intelligence reports mentioned mysterious new equipment, but captured aircrews provided no information. British aircrew were under strict orders regarding new radar technology, knowing that capture of the devices intact could compromise Allied superiority that had been years in development. Aircrew were briefed that H-2S equipment was so valuable that its loss to the enemy could change the course of the war. Instructions were clear: reveal nothing, even under interrogation. The self-destruct charges installed in H-2S units were designed to trigger automatically on severe impact or could be manually activated if capture seemed imminent. In December 1942, German signals intelligence detected unusual radio emissions from RAF bombers during raids. The signals were brief, pulsed transmissions at frequencies around 3 gigahertz, corresponding to wavelengths near 9 centimeters. German radio engineers who examined the intercept reports dismissed the initial findings. No one could generate useful power at such frequencies, the physicists insisted. The laws of physics, as understood by German researchers, made high-power centimetric radar impractical. The emissions must be some form of electronic countermeasure, perhaps a decoy transmitter, or possibly navigational beacons on the ground being interrogated by airborne receivers. They could not be operational radar because that would require power outputs German theory indicated were unachievable. On January 30th, 1943, RAF Bomber Command conducted its first operational mission using the new H-2S ground mapping radar. 13 aircraft equipped with the centimetric radar from Pathfinder Force marked targets in Hamburg. Actually, only 6 aircraft completed the marking mission, as 7 had to turn back with technical difficulties. The raid succeeded despite weather conditions that would have scattered conventional bombing. Observers noted the precision of the attack despite 10/10 cloud cover. The Pathfinders had marked the target with incendiary indicators, and 100 Lancasters that followed bombed using these visual markers. For the first time, RAF bombers had found and marked a target in complete darkness and total cloud cover using only electronic navigation. The Luftwaffe achieved several interceptions during the Hamburg raid. 1 bomber was shot down, but the H-2S equipment aboard was destroyed in the crash and subsequent fire. German investigators found fragments of unusual radio equipment in the wreckage, but nothing that revealed the system's full capability or operating principles. They were looking at pieces of the most advanced radar technology in existence and did not recognize what they were seeing. The fragments showed evidence of centimetric wavelength components, but without a complete system, German analysts could not determine the purpose or capabilities of the equipment. 4 days later, on the night of February 2nd and 3rd, 1943, the technological revelation arrived in a field near Rotterdam. The RAF conducted a raid on the Pernis oil refineries near Rotterdam. Short Stirling Mark TA-1 bomber R9264, serial number MGL, nicknamed Life for Love, from No. 7 Squadron Pathfinder Force, was returning from a bombing mission to Cologne when it was intercepted. Oberleutnant Hans-Dieter Frank of 2, NJG-1, flying a Messerschmitt Bf-110 from Gilse Region Airfield, closed on the bomber in darkness. Ground-controlled interception using Würzburg radar had vectored the night fighter to the bomber's position. Feldwebel Wilhelm Gotter, Frank's radar operator, confirmed the target on their Liechtenstein airborne radar. The engagement was textbook. Frank positioned his Bf-110 below and behind the Stirling, in the blind spot where the bomber's defensive guns could not engage. A burst from the upward-firing cannon struck the bomber's fuselage and wing. The Stirling went down trailing fire, crashing at 22:01 hours near Hendrik Ido Ambacht, approximately 3 kilometers from the village of Humsted. The impact was severe but not catastrophic. The aircraft did not explode on impact, though fire quickly spread through the wreckage. German recovery teams reached the crash site before dawn. 5 crew members had been killed in the crash, including squadron leader William Arthur Smith. 2 crew members survived and were taken prisoner. In the shattered nose section of the bomber, recovery personnel found equipment unlike anything in German experience. A rotating parabolic antenna, barely 60 centimeters in diameter, was connected to an electronic chassis that included a circular cathode ray tube display showing a plan position indicator format. The display unit had been destroyed in the crash, the glass tube shattered, and internal components damaged beyond repair. But the transmitter section survived largely intact, protected by its robust copper construction. At the heart of the transmitter was that copper cylinder, machined with extraordinary precision, containing 8 symmetrical cavities arranged around a central cathode. The device was labelled with British military markings and the designation CV64. It was sealed, self-contained, with no external power connections beyond the primary electrical feed and a simple output coupling. The engineering was elegant, almost deceptively simple in appearance, yet the precision of manufacturing was immediately apparent even to initial examination. This was not experimental equipment hastily assembled in a laboratory. This was production hardware designed for reliability and manufactured to exacting standards. General Lieutenant Wolfgang Martini, head of Luftwaffe Signals Intelligence, arrived at the crash site later that morning. Martini was not merely an administrator, but a trained engineer who understood radar technology. He had followed German radar development closely and was familiar with the theoretical limitations that had guided German research priorities. When he examined the captured equipment, he understood immediately that this was significant. The equipment was compact beyond anything German radar could achieve. The antenna was far too small for operation at frequencies Germans considered practical for high-power applications. Yet this was clearly sophisticated technology, not some experimental oddity that had failed under operational conditions. This was a working system that had been operating successfully when the bomber was shot down. Martini ordered the equipment transported under armed guard to Telefunken's Berlin laboratories. The magnetron was packed with extraordinary care. Guards accompanied the transport throughout the journey. The importance of the capture was immediately recognized at the highest levels of Luftwaffe command. This was not routine battlefield salvage, but a potential intelligence windfall that could reveal Allied technological capabilities. Professor Leo Brandt received the recovered components on February 3rd at Telefunken's facilities in Berlin-Tempelhof. Brandt, born in 1908, had worked as a high-frequency engineer at Telefunken since 1932. He was recognized as one of Germany's leading experts in radio frequency technology. His team worked through the night of February 3rd and 4th, meticulously documenting the device before attempting any testing. Every dimension was measured. Every component was photographed from multiple angles. Detailed sketches were made of the internal structure visible through inspection ports. X-ray examination revealed the internal cavity structure and cathode assembly. The team worked with scientific precision, documenting everything because they understood they might have only one opportunity to examine this technology. What they found in those initial hours stunned them. The magnetron was a sealed unit, entirely self-contained, with no external magnets. German magnetron designs, including Hollmann's patented versions, required separate, powerful electromagnets to generate the magnetic field necessary for operation. These electromagnets were large, heavy, and required substantial electrical power. This device had permanent magnets built into its structure, integrated directly into the copper block housing. The magnets appeared to be made from cobalt steel alloys, materials that provided magnetic field strength. German researchers had considered impossible to achieve with permanent magnets. The engineering was elegant to the point of appearing simple, but the precision required was extraordinary. Tolerances were measured in hundredths of millimeters. The 8 cavities were machined into solid copper blocks, not assembled from separate components. Each cavity was identical to the others within measurement precision. The cathode, running along the central axis, was coated with an oxide compound that German researchers recognized as an electron-emitting surface, but of a type German industry had not successfully manufactured. The vacuum seals used techniques that German manufacturers had attempted but not mastered for production units. Every gasket, every junction, every mechanical interface showed evidence of manufacturing processes refined through extensive production experience. On February 4th, Brandt's team prepared to power the magnetron. They built a custom pulse generator to provide the high-voltage electrical pulses needed for operation. The team had no documentation, no operating instructions, no specifications. They had to infer the operating parameters from examination of the device and from general principles of magnetron operation. They expected, based on German experience with magnetron development, perhaps 100 watts output at best, possibly at frequencies around 500 megahertz. They thought they understood the limitations of the technology. When the magnetron was powered for the first time in a German laboratory, it produced approximately 10 kilowatts of pulsed power at precisely 3 gigahertz. The output was stable, repeatable, and far exceeded what German theory predicted as possible. The measurement instruments available in the laboratory were designed for much lower power levels. They had to improvise measuring techniques, using attenuators to reduce the signal to levels their equipment could handle, then calculating back to determine the actual output power. Every measurement confirmed the same incomprehensible reality. This thumb-sized device generated more microwave power than German laboratory equipment filling entire rooms could produce, and it did so with an efficiency German theory suggested was unattainable at these frequencies. Brandt wrote in his initial report, preserved in German archives and later captured by Allied intelligence teams, that the British had achieved in practice what German mathematics declared impossible. The report's tone was professional, clinical even, but the implications were clear to anyone who read it. Germany's understanding of microwave physics was incomplete. The theoretical frameworks that had guided German research had led them away from a technology that was not only practical, but had been in operational use by the enemy for an unknown period. Engineers measured the magnetron's performance over several days of testing. The output frequency was remarkably stable, varying less than 1% across multiple tests. The frequency stability was achieved through the physical dimensions of the cavities themselves, which acted as resonant structures. German magnetrons, using Hollmann's design, suffered from frequency drift as the device heated during operation, thermal expansion changing the electrical properties of the oscillating system. The British design minimized this through careful engineering of the mechanical structure and choice of materials with appropriate thermal expansion coefficients. Every measurement revealed another layer of sophisticated engineering. The wavelength was equally shocking from a military applications standpoint. 9 centimeters corresponded to 3 gigahertz frequency. At this wavelength, a small antenna could provide resolution that would require antenna arrays tens of meters across at frequencies Germany used. The implications for airborne radar were immediate and devastating. The British could build radar systems compact enough for single-engine fighters, with resolution fine enough to detect individual buildings from high altitude. They could create ground-mapping radar that showed coastlines, rivers, cities, and terrain features with clarity impossible at longer wavelengths. They could detect submarine conning towers, night fighters, and ships with precision that made German longer wavelength radar seem primitive by comparison. German radar development had dismissed centimetric wavelengths as impractical, precisely because they could not generate sufficient power. The entire German radar research program had been built on the assumption that high-power microwave generation was impossible, or at least impractical for military applications. The British had solved that problem 3 years earlier, in February 1940, when John Randall and Harry Boot at Birmingham University produced their first working prototype, generating 400 watts at 9.8 centimeters wavelength. By May 1940, they had improved that to over 1 kilowatt. By late 1940, General Electric Company engineers at Wembley had increased output to 10 kilowatts, and by 1941, production magnetrons were achieving over 100 kilowatts in pulsed operation. On February 5th, a conference was convened at Luftwaffe headquarters in Berlin. The meeting was classified at the highest level. Present were General Lieutenant Martini, Professor Brandt, representatives from Telefunken, Siemens, and GEMA, the major German electronics firms, plus air defense commanders and Luftwaffe technical staff. The mood was somber. Brandt presented his findings methodically, using technical language and precise measurements, but the conclusions were inescapable. The British cavity magnetron represented not an incremental advance, but a fundamental technological breakthrough that Germany had missed entirely. German scientists had worked on magnetron designs. Hollmann's patents proved German researchers understood the basic principles. But German research had abandoned high-power microwave development because mathematical models indicated it was not feasible within wartime timescales. Resources were limited. Industry was strained. Priority went to improving existing systems rather than pursuing speculative technologies that physicists said would not work. The British had not just solved the engineering challenges, They had been operating centimetric radar operationally for months, possibly years, while Germany remained convinced such technology was theoretically impossible or at minimum years away from practical implementation. The conference reviewed what was known about British radar deployment. The Würzburg system had successfully intercepted numerous RAF bombers. Recovery teams had examined wreckage and found no evidence of advanced radar equipment in aircraft shot down before January 1943. This suggested the H-2S deployment was recent, but intelligence from other sources painted a more troubling picture. Reports from U-boat commanders described being surprised by aircraft attacks in conditions where detection should have been impossible. Kriegsmarine intelligence had noted increasing Allied success in locating surfaced submarines. Luftwaffe bomber crews reported being intercepted by British night fighters with suspicious frequency. The conference participants began connecting disparate intelligence reports into a coherent picture. The British had developed not just one centimetric radar system, but an entire family of applications: ground mapping radar for bomber navigation, air-to-surface vessel radar for submarine detection, airborne interception radar for night fighters, possibly a gun-laying radar for anti-aircraft systems. Each application used the same basic technology, the cavity magnetron, adapted for specific military purposes. The British had not achieved one breakthrough. They had created an entire new category of radar technology, while Germany was still perfecting longer wavelength systems. The captured system was given the designation Rotterdam Gerät, the Rotterdam Device, named for the location of the crash. A working group formed immediately, the Arbeitsgemeinschaft Rotterdam, abbreviated AGR. The group's mandate was threefold. First, understand how the British magnetron achieved its performance. Second, develop countermeasures against centimetric radar to protect German forces. Third, begin German development of equivalent technology to close the gap the British had opened. Each objective faced substantial obstacles that would prove increasingly difficult to overcome as the war situation deteriorated. Understanding the magnetron required reverse engineering manufacturing processes Germany had not developed. The device used oxide-coated cathodes requiring specific materials and processing techniques. German vacuum tube manufacturers had attempted to produce similar cathodes, but had not achieved consistent results in production. The British had clearly solved the manufacturing problems through years of development and production experience. The permanent magnets required cobalt, a strategic material Germany had in limited supply. Before Operation Barbarossa, Germany had received cobalt from Soviet sources, but that supply was cut off when Germany invaded the USSR. Turkish imports partially compensated, but supplies remained insufficient for large-scale production. Even the vacuum sealing techniques were unfamiliar to German manufacturers. The magnetron had to maintain high vacuum over extended operating life, while withstanding vibration, temperature changes, and mechanical stress of operational use. German vacuum tube manufacturing used glass envelopes with metal-to-glass seals, techniques perfected over decades for radio tubes. The British magnetron used all-metal construction with ceramic insulators, requiring entirely different manufacturing approaches. Every aspect of the device revealed engineering refinements that came only from extended production experience. On February 22nd and 23rd, the Arbeitsgemeinschaft Rotterdam held its first formal two-day meeting at Telefunken's offices in Berlin. Present were representatives from Germany's electronics industry, Luftwaffe technical services, university researchers, and radar specialists from operational units. The group examined the magnetron in exhaustive detail, passing the device around the conference table, taking measurements with calipers and micrometers, making sketches, discussing manufacturing challenges. The atmosphere was professionally subdued. These were experienced engineers and physicists who understood exactly what they were looking at and what it meant. The consensus was sobering. Germany could copy the British design. German machine shops, given proper tooling and sufficient time, could manufacture components to the required tolerances. German materials scientists could develop equivalent cathode coatings. German metallurgists could create permanent magnets approaching British performance, but production would require diverting resources from existing programs that were already struggling to meet Wehrmacht demands. Manufacturing capacity for precision components was strained to breaking. Machine tools were operating multiple shifts. Skilled workers were in short supply, increasingly being drafted for military service. Raw materials were allocated months in advance to existing priority programs. Introducing entirely new production processes for unfamiliar technology would take many months at minimum, possibly over a year before meaningful production quantities could be achieved. Dr. Otto Hachenberg, a young Telefunken engineer assigned to the AGR project, later recalled the atmosphere in those early meetings during a 1973 interview conducted by Woodruff Sullivan for the National Radio Astronomy Observatory. The interview was part of Sullivan's research for his book on early radio astronomy. Hachenberg, who had worked on recovering and analyzing radar equipment from crashed Allied aircraft during the war, described the psychological impact of examining the British technology. We were examining equipment that proved British engineers had solved problems we had declared unsolvable. Every aspect of the design revealed thoughtful engineering, matured through experimentation we had never conducted. This was not prototype equipment cobbled together in a laboratory. This was production hardware, implying the British had been manufacturing these devices in quantity. We were studying what appeared to be the third or fourth generation of their development, while we had not begun serious work on the first generation. The revelation was compounded when interrogators interviewed the surviving crew members from the downed Sterling. Initially, the two prisoners provided only name, rank, and serial number, as required by Geneva Convention. They had been extensively briefed on the importance of the H2S system and understood that no information should be disclosed. RAF Bomber Command had emphasized during briefings that H2S represented years of British research investment and that its capture by Germany could compromise Allied bombing effectiveness. Aircrew were told that under no circumstances should they discuss the radar system's capabilities, operating principles, or deployment status. However, over subsequent days and weeks, German interrogators skillfully extracted key details. The Luftwaffe Interrogation Center, Auswertestelle West at Oberursel near Frankfurt, employed experienced interrogators who used sophisticated psychological techniques. The interrogators did not resort to physical coercion, which was generally counterproductive with Allied aircrew and violated Wehrmacht policy. Instead, they used a combination of isolation, seemingly casual conversation, planted false information to elicit corrections, and careful psychological pressure applied over extended periods. From these interrogations, German intelligence learned critical information. The system was called H2S, though the prisoners did not know the origin of the designation. It provided a map-like display of ground features below the aircraft, showing coastlines, cities, rivers, and terrain. The radar had been in operational service since late January 1943, only days before this particular aircraft was shot down. Most alarmingly, the crew indicated this was not experimental equipment assigned to a few select aircraft. Bomber Command was in the process of fitting H2S to the entire Pathfinder force initially, with plans to eventually equip all heavy bombers. The prisoners' information suggested British production capacity was sufficient to manufacture these devices in hundreds, possibly thousands. The scale of British centimetric radar deployment became clearer as intelligence accumulated through February and March 1943. Multiple sources of information began converging into a comprehensive picture. Signals intelligence detected H2S transmissions from increasing numbers of RAF bombers. The distinctive pulse characteristics and frequency range became identifiable. Kriegsmarine reports documented increasing U-boat losses in the Atlantic, with submarines being attacked by aircraft in conditions where detection by previous generation radar should have been impossible. Submarines were being caught surfaced at night in complete darkness, attacked before they could crash dive to safety. The magnetron technology was not limited to bombing radar. Coastal Command aircraft were using centimetric ASV Mark III radar to detect surfaced submarines. The same cavity magnetron that provided 9 cm wavelength for H2S ground mapping could detect submarine conning towers and periscopes at ranges that longer wavelength radar could not match. The narrow beam width possible at centimetric wavelengths provided angle accuracy sufficient to guide aircraft directly to submarines before detection was possible using German METOX radar detectors, which were tuned to detect the longer wavelengths of ASV Mark II radar. U-boat losses in the Atlantic had been climbing mysteriously throughout late 1942 and early 1943. Admiral Karl Dönitz, commanding U-boat forces, had noted with concern that submarines were being caught on the surface with increasing frequency. U-boat commanders reported being attacked by aircraft that appeared suddenly, providing no warning that allowed time to dive. The METOX detector, which had previously provided effective warning of approaching ASV-equipped aircraft, was failing to detect these new attacks. The explanation was now clear. British aircraft were hunting submarines using ASV Mark III centimetric radar that German boats could not detect with existing equipment. British night fighters were equipped with centimetric AI radar designated AI Mark VIII, far superior to German Liechtenstein systems. German Liechtenstein Fug 202 operated at 61 cm wavelength and required large 32-element Matratze antenna arrays that created significant aerodynamic drag and reduced aircraft speed by 20 to 30 km per hour. The later Liechtenstein SN2 used lower frequency to avoid British jamming, but required even larger 8-element Hirschgeweih antenna arrays that slowed aircraft by 50 km per hour. British centimetric AI used compact dish antennas barely 1 meter in diameter and provided superior target resolution with minimal aerodynamic penalty. RAF night fighters equipped with AI Mark VIII had been decimating German bomber raids over Britain throughout early 1943, and Luftwaffe intelligence had attributed this to improved ground-controlled interception tactics and searchlight cooperation. The real reason was radar that could locate German bombers with precision German technology could not match. On March 1, 1943, the situation took an ironic turn that would be almost comedic if the stakes were not so serious. During a major RAF raid on Berlin, British bombs struck Telefunken's Berlin facility, where the Rotterdam Garret was being analysed. The building suffered severe damage. The captured magnetron was destroyed, blown to fragments by the explosion. The working group lost its only complete sample just as they were beginning to understand its construction and preparing to attempt production copies. The loss was devastating. Weeks of careful analysis, documentation, and reverse engineering planning seemed wasted. Then, extraordinarily, that same raid provided a replacement. Handley Page Halifax II W7877, serial TLO from No. 35 Squadron, was shot down by Lieutenant August Geiger near Markelo in the Netherlands. The Halifax crashed with another H2S unit aboard. Recovery teams found the equipment in better condition than the Rotterdam Device, with much of the display system intact along with a complete magnetron. The odds of losing one sample to bombing and gaining another on the same night were astronomical, but it illustrated the scale of British H2S deployment. RAF Bomber Command was equipping aircraft with this advanced technology at a rate suggesting substantial manufacturing capacity existed. German scientists immediately set to work analysing the second unit. The device was essentially identical to the Rotterdam Garret, confirming these were production units manufactured to standard specifications rather than hand-built prototypes. Telefunken was tasked with producing German copies designated LMS-10 based on the British CV64 design. The designation LMS stood for Laufzeitröhre mit Magnetsteuerung, transit time tube with magnetic control. The copying process revealed a layer upon layer of British engineering sophistication that would challenge German manufacturing capabilities. Every component required manufacturing processes that German industry had to develop from scratch or significantly improve. The cavity dimensions had to be machined to extraordinary precision. Tolerances of 0.02 mm or better were required to achieve proper resonance at the operating frequency. German machine shops, accustomed to tolerances of 0.1 mm for most radar components, were not equipped for such precision work on the required scale. New milling machines with better bearings and more rigid construction had to be procured. Precision measuring instruments had to be calibrated. Machinists had to be trained in techniques they had not previously needed. The entire manufacturing process required improvements German industry struggled to implement while simultaneously dealing with Allied bombing disruption. The oxide-coated cathodes required materials and processes that German chemical industry had not perfected. British cathodes used barium and strontium oxide coatings applied at high temperature in precisely controlled atmospheres. The coating had to be uniform, adherent, and produce consistent electron emission properties. German attempts to produce similar cathodes had been partially successful in laboratories, but had not achieved the consistency needed for production units. British manufacturers clearly had years of production experience refining the process. German industry was starting from laboratory-level understanding and attempting to reach production-level capability under wartime pressures. Britain had been working with American firms, particularly Western Electric and General Electric, that had decades of experience with vacuum tube manufacturing for communications and broadcasting applications. When Britain shared cavity magnetron technology with the United States through the Tizard mission in September 1940, American 2004, manufacturers had rapidly scaled up production using manufacturing expertise gained through years of commercial vacuum tube production. Germany had strong vacuum tube industry, but it was oriented toward glass envelope construction using metal-to-glass sealing techniques. The all-metal magnetron with ceramic insulators required different manufacturing approaches that German industry was attempting to develop in parallel with production efforts. The permanent magnets presented perhaps the greatest material challenge. British magnetrons used cobalt steel alloys, likely Alnico type, to create powerful permanent magnets integrated directly into the tube structure. These magnets provided magnetic field strength of several thousand Gauss, necessary for proper magnetron operation. Germany faced critical cobalt shortages that affected all high-temperature alloy production. Cobalt was essential for turbine blades in aircraft engines, cutting tools for machine shops, and various steel alloys used in weapons production. Before the war, Germany had imported cobalt primarily from Belgian Congo and Canada. Sources cut off when war began. Limited supplies came from Finland and Turkey, but quantities were insufficient to meet all military needs. Diverting cobalt to magnetron production meant reducing availability for other military necessities, each with its own priority claim on scarce resources. German planners faced impossible allocation decisions. Aircraft engine manufacturers needed cobalt for turbo-supercharger components that allowed high-altitude operation. Machine tool manufacturers needed cobalt steel for cutting tools that maintained hardness at high temperatures. Tank manufacturers needed cobalt for armor-piercing ammunition. Every ton of cobalt allocated to magnetron magnets was a ton unavailable for these competing uses. German engineers experimented with alternative magnetic materials, including various iron-nickel alloys and chrome-steel combinations. None provided the field strength required for optimal magnetron performance. Electromagnets could provide sufficient field strength but added weight, required separate power supplies, and introduced reliability issues. The elegance of the British design, with integrated permanent magnets requiring no power and having no failure modes, was impossible to replicate with German materials. In a bitter irony that illustrated the desperate state of German radar development, engineers began salvaging permanent magnets from other crashed British aircraft to complete their magnetron copies. German production units were being completed using British-manufactured components cannibalized from battlefield salvage, a situation that underscored the industrial limitations Germany faced. By May 1943, Telefunken had completed 4 LMS-10 magnetrons, painstaking copies of the British CV64 design. These represented 3 months of intensive work by some of Germany's best engineers and consumed resources from precision machine shops, chemical plants, and materials suppliers across German industry. 4 tubes total. Meanwhile, according to captured documents recovered after the war, Britain was producing approximately 200 cavity magnetrons per month by mid-1943, and American production was reaching similar levels. The disparity was not just technological, it was industrial, reflecting fundamentally different manufacturing capacities and resource availability. Germany could understand the technology. German physicists grasped the operating principles. German engineers could design equivalent systems on paper, but Germany lacked the manufacturing base to produce the technology at scale while simultaneously maintaining production of existing military equipment. The Arbeitsgemeinschaft Rotterdam continued meeting throughout spring and summer 1943, developing detailed production plans, requesting resource allocations, and attempting to overcome manufacturing bottlenecks. But practical progress remained, frustratingly slow as Germany's industrial situation deteriorated under Allied bombing and resource exhaustion. Meanwhile, the AGR pursued parallel efforts on countermeasures against centimetric radar. If Germany could not match British capability immediately, they could develop systems to detect and counter it, reducing the operational advantage British radar provided. The detection effort proved relatively straightforward compared to magnetron production. Crystal detectors tuned to 9 cm wavelengths could pick up H2S transmissions at considerable range. German industry could manufacture crystal detectors using existing technology. No exotic materials were required. No new manufacturing processes needed development. By April 1943, German engineers had developed prototype detectors that night fighters could carry. The system was designated Fug 350 Naxos Z, named after the Greek island Naxos. The device used a rotating direction-finding loop antenna housed in a teardrop-shaped fairing mounted on aircraft fuselages. The receiver covered the frequency range 2,500 to 3,750 MHz, encompassing the H2S operating frequency. Detection range was approximately 35 kilometers, sufficient to allow night fighters to locate bomber streams that were otherwise invisible in darkness and clouds. Naxos provided night fighter crews with general direction to RAF bombers using H2S. The system could not provide precise range or bearing information, but it allowed fighters to home toward emission sources, then use visual observation or Liechtenstein AI radar for final intercept. Naxos entered operational service in September 1943, first used operationally on September 2nd. German night fighter kills increased as pilots learned to home on H2S emissions, treating the British radar transmissions as a beacon that revealed bomber locations. However, Naxos was fundamentally reactive technology, a countermeasure against British capability rather than an equivalent German system. It relied entirely on British bombers transmitting. If the British turned off their radar or used different frequencies, Naxos was useless. British intelligence soon learned of Naxos through signals intelligence and prisoner interrogation. RAF worried that H2S was revealing bomber positions to German fighters, possibly causing losses that outweighed the navigation benefits. A detailed analysis was conducted comparing bomber loss rates before and after Naxos deployment. Surprisingly, analysis showed losses actually decreased slightly after Naxos introduction, possibly because H2S-equipped aircraft could navigate more accurately and spend less time over German territory. RAF concluded H2S benefits outweighed the risks and continued full deployment. British engineers immediately began developing countermeasures, including 3 cm H2S Mark III that would operate outside Naxos detection range. German efforts at developing indigenous centimetric radar moved forward slowly through 1943 and 1944, facing mounting obstacles as Germany's strategic situation deteriorated. Telefunken worked on an airborne interception radar designated Fug 240 Berlin using copied magnetron technology. The system was intended to provide German night fighters with centimetric AI capability, matching British systems. Siemens developed a ground-based jammer called Roderick, intended to interfere with H2S operations by transmitting strong signals on H2S frequencies. GEMA investigated centimetric early warning systems to replace Freya with more capable technology. Every project faced the same fundamental constraints that would prove insurmountable. Limited manufacturing capacity meant that even when prototype systems worked, production could not be scaled up rapidly. German industry was already operating at maximum capacity, producing existing radar systems, communications equipment, and other electronics. There was no spare capacity to absorb new production programs. Shortage of critical materials worsened throughout 1943 and 1944 as Allied bombing disrupted supply chains and cut access to sources. Cobalt for magnets, tungsten for transmitter tubes, special steel alloys for waveguide components. Even basic materials like copper and aluminum became increasingly difficult to obtain in necessary quantities. Lack of experience with high-frequency techniques meant German engineers were learning as they developed systems. Components that British engineers considered standard were exotic rarities in Germany, requiring development programs for each component type. Crystal mixers for receivers required germanium crystals ground and mounted with precision German industry could not consistently achieve. The crystals had to be contacted precisely to create a metal semiconductor junction with proper electrical characteristics. British manufacturers, working with American partners, had standardized crystal detector production. German manufacturers were still perfecting laboratory techniques. Waveguide components needed machining accuracy beyond normal German manufacturing standards. Waveguides, hollow metal tubes conducting microwave energy, required precise internal dimensions to propagate desired frequencies without excessive loss. Surface finish requirements were more stringent than for lower-frequency RF components. German machine shops struggled to meet specifications consistently. Even relatively simple items like coaxial cables designed for centimetric wavelengths were in short supply. The cables required precise conductor spacing maintained over the cable length, with low-loss dielectric materials and proper shielding. German cable manufacturers, oriented toward lower frequencies, had difficulty achieving necessary performance. The comparison with British and American capabilities became clearer as more intelligence arrived through various sources. The TISAD mission to America in September 1940 had shared cavity magnetron technology with the United States, demonstrating the device to American scientists at meetings in Washington, D.C. The demonstration of the magnetron, which occurred on September 19, 1940, at Alfred Loomis's apartment in Washington's Wardman Park Hotel, had stunned American researchers. The British magnetron produced 100 times more power than anything Americans had achieved at centimetric wavelengths. American scientists immediately recognized the technology's military significance. American industrial capacity had rapidly mobilized to exploit the technology. The Radiation Laboratory was established at MIT in November 1940, specifically to develop radar systems using cavity magnetron technology. The lab grew to over 4,000 scientists and engineers by 1943, an organizational scale Germany could not match. Contracts had been placed with dozens of American manufacturers for magnetron production. Bell Telephone Laboratories, Western Electric, Westinghouse, General Electric, RCA, and many smaller firms were producing magnetrons and radar components. By 1943, American industry was producing magnetrons at rates of thousands per month, equipping not just American forces but also supplying Britain through Lend-Lease. The magnetron that German scientists examined with such care was one of tens of thousands being manufactured. America was incorporating centimetric radar into every conceivable military application. Gun-laying systems like the SCR-584 used centimetric radar to direct anti-aircraft fire with unprecedented accuracy. Naval fire control systems used centimetric radar to spot shell splashes, and direct gunfire onto targets beyond visual range. Airborne early warning systems using centimetric radar detected enemy aircraft at ranges exceeding 150 kilometers. Precision bombing aids like LAB used centimetric radar with autopilot integration to automatically bomb through clouds. Each application represented development programs with budgets measured in millions of dollars, exceeding Germany's entire radar research allocation for all programs combined. British centimetric radar production had expanded from laboratory prototypes in 1940 to industrial-scale manufacturing by 1942. The GEC facility at Wembley had manufactured the early prototype magnetrons that went to America on the Tizard mission. By 1942, GEC, EMI, Ferranti, Standard Telephones and Cables, and other British firms were producing magnetrons by hundreds monthly. The cavity magnetron had become a production component with standardized designs, interchangeable parts, and quality control procedures, ensuring consistent performance batch after batch. British manufacturers had solved the production engineering problems that German industry was still attempting to overcome. German magnetron development remained in the experimental stage, producing hand-built prototypes that required individual tuning and adjustment. Every German magnetron was unique, built by skilled technicians who adjusted cavity dimensions, cathode positioning, and magnetic field until performance met specification. This was laboratory practice, not industrial production. British magnetrons came off production lines with performance specifications guaranteed by manufacturing process control. Dimensions were held by precision machining. Cathode coatings were applied using controlled processes yielding consistent results. Magnets were manufactured to specifications ensuring proper field strength. Testing verified performance, but individual tuning was not required because the manufacturing process ensured consistency. The difference represented not just years of development time but entirely different approaches to industrial organization and quality control. As German scientists struggled with magnetron production, they also began understanding how far behind they had fallen in related technologies beyond the magnetron itself. Cavity magnetrons enabled compact centimetric radar, but effective systems required other technologies equally advanced. British radar used plan position indicator displays, circular cathode ray tube screens showing a map-like presentation of targets with the radar at the center and targets appearing at proper range and bearing. This was far more intuitive than A-scope displays showing range and bearing separately. German radar relied on A-scope displays because that was the established technology, well understood and producible. Developing PPI displays required specialized CRT tubes, deflection circuits, and signal processing that German radar engineers were only beginning to investigate seriously in 1943. British systems incorporated automatic tracking, using servo mechanisms to keep antennas locked on targets without manual operator control. Once a target was acquired, the radar tracked automatically, maintaining lock through turns and maneuvers. German systems required manual tracking by skilled operators who adjusted controls to keep targets centered on displays. Automatic tracking required feedback control systems, position servos, and signal processing techniques that German industry had not widely deployed. The technology existed in German laboratories, but production systems remained manually operated. British radar used TR switches, transmit-receive switches, devices allowing a single antenna to both transmit and receive by isolating the receiver during transmission pulses. This eliminated the need for separate transmit and receive antennas, simplifying antenna systems and improving performance. German systems typically used separate antennas or simple switching methods that were less effective. British TR switches used gas discharge tubes that switched in nanoseconds, protecting sensitive receivers from kilowatts of transmitter power. German engineers were beginning to develop similar components in 1943, but were years behind in practical implementation. The most troubling aspect of the technological gap was how it had developed largely invisibly to German intelligence. Germany had excellent scientists, many trained at world-class universities. Germany had capable engineers with strong theoretical backgrounds. Germany had substantial industrial capacity built up through the 1932 rearmament program. Yet Britain, with significantly smaller industrial base and fewer total resources, had achieved decisive technological superiority in the most militarily significant electronic technology of the war. Understanding how this occurred became a subject of post-war analysis that revealed important lessons about technology development and strategic planning. The explanation lay in different strategic decisions made years earlier, before the war began. Britain had prioritized radar development from 1935 onward, under the direction of Robert Watson Watt and the Committee for the Scientific Survey of Air Defense. Substantial government funding flowed to radar research. The chain-home early warning system was built despite being expensive and technically challenging. Research infrastructure was created specifically for radar development, including the Bordsey Research Station and later the Telecommunications Research Establishment. Specialists were trained systematically. Industrial capacity was built up with government support. By 1939, Britain had invested years of effort and substantial resources in radar technology. Germany had also developed radar systems in the 1932, actually deploying operational systems before Britain in some cases. The Freya and Würzburg radars were excellent systems, but Germany had not made radar development the top national priority that Britain had. German radar programs competed with numerous other military technology programs for funding and resources. When war began, German industry focused on producing existing systems rather than exploring new approaches. The Blitzkrieg victories of 1939 to 1941 seemed to validate German equipment and tactics, reducing pressure to develop fundamentally new technologies. The Hitler Decree of 1940, limiting research funding to projects promising results by 1942, had been particularly devastating for long-term radar development. Cavity magnetron development required patient experimental work over multiple years. Gradual refinement of manufacturing processes could not be rushed. Systematic testing was needed to understand behavior at frequencies that existing theory inadequately explained. Such research could not promise definite results within the 2-year timeframe the decree mandated. German programs exploring centimetric wavelengths were defunded or reduced in priority in 1940 and 1941, precisely when British programs were achieving breakthrough results. German research facilities were shifted to improving existing systems rather than developing fundamentally new capabilities. Würzburg improvements, Freya range extensions, Liechtenstein airborne radar development all received priority because they promised near-term operational improvements. Longer-range research into fundamentally different approaches was postponed until after victory, which German leadership expected to achieve through existing capabilities. The decision was rational given German military success in 1940 to 1941 and the apparent vindication of German equipment and tactics. But it conceded technological initiative to Britain at the critical moment when British desperation was driving innovation. By summer 1943, the full scope of Allied centimetric radar deployment was apparent to German air defence through accumulated intelligence from multiple sources. British H-2S enabled precision bombing through weather and darkness that previously scattered bombing effectiveness. Over 200 RAF bombers were equipped with H-2S by mid-1943, with production continuing at rates that would equip the entire heavy bomber force within a year. Coastal Command ASV Mark III radar was making the Atlantic progressively more dangerous for U-boats, contributing to a crisis that would force Dönitz to temporarily withdraw U-boats from the North Atlantic in May 1943. RAF night fighters with centimetric AI Mark VIII were inflicting unsustainable losses on German bomber forces, attempting attacks on Britain, essentially ending the German strategic bombing campaign. American radar technology was advancing even faster than British, with development programs that dwarfed British efforts in scale. The SCR-584 gun-laying radar, using cavity magnetron technology and automatic tracking, was achieving anti-aircraft effectiveness previously impossible. Naval surface search radars were allowing American ships to fight effectively in darkness and poor visibility. Airborne early warning radar was providing fleet protection against air attack. Each American system represented development programs with budgets and personnel that exceeded Germany's entire radar effort. The Manhattan Project analogy became common in post-war German memoirs. Germany had excellent nuclear physicists, including Werner Heisenberg, Otto Hahn, and others of international reputation. But Germany was years away from atomic weapons, if such weapons could be built at all. German nuclear research had been fragmented, underfunded, and lacked the massive industrial mobilization that characterized the Manhattan Project. Similarly, Germany had excellent radar engineers and physicists. But Germany was a decade behind in the specific technology that dominated electronic warfare. The cavity magnetron gap was not just technological. It represented comprehensive failure in scientific industrial mobilization for a technology whose military significance was not recognized until Britain had already achieved insurmountable lead. German attempts to close the gap continued through late 1943 and 1944. But circumstances were increasingly unfavorable. Allied bombing was disrupting German industrial production systematically. The combined bomber offensive specifically targeted ball-bearing factories, aircraft plants, oil refineries, transportation networks, and electronics manufacturing facilities. Material shortages worsened as sources were cut off and stockpiles depleted. Romanian oil production was threatened. Swedish iron ore supplies were reduced. Turkish chrome and cobalt deliveries became irregular. Every critical material faced allocation problems. Skilled workers were being drafted for combat units as military losses mounted and frontline units demanded replacements. Engineers and technicians were conscripted, taking specialized knowledge out of factories and laboratories. Training new workers took time Germany did not have. Quality suffered as experienced workers were replaced by hastily trained substitutes. Research facilities were being evacuated from cities vulnerable to air attack, disrupting ongoing programs and scattering teams. The Telefunken facilities in Berlin were bombed multiple times. The AGR itself had to relocate meetings to different locations as facilities were damaged or destroyed. The Arbeitsgemeinschaft Rotterdam continued meeting throughout 1943 and 1944, documenting progress and obstacles in detailed protocols that survived the war and provided historians with insight into German radar development struggles. Meeting minutes show technical discussions of magnetron design, manufacturing problems, materials shortages, and mounting frustration with lack of progress. The protocols reveal competent engineers working under impossible conditions, understanding what needed to be done but lacking resources and time to accomplish it. Production plans were developed, showing how Germany could manufacture magnetrons in militarily significant numbers if materials were available, if skilled workers could be retained, if bombing did not disrupt production, if enough time existed. None of those conditions could be met. By early 1944, Telefunken had produced approximately 20 magnetron copies, compared to over 10,000 produced by British and American industry. Siemens had delivered a handful of Roderick jammers that were deployed at air defense sites around key targets, but their effectiveness was limited. The Berlin airborne radar remained in extended testing, encountering problems with reliability and performance. Production of operational systems in militarily significant numbers remained perpetually 6 months away, a timeline that kept receding as obstacles mounted. In April 1945, as Allied forces overran German territory from east and west, Telefunken finally began delivering production Fug 240 Berlin night fighter radars. The system used German-built magnetrons based on captured British designs and provided capabilities roughly equivalent to British centimetric AI from 1942, 3 years earlier. About 25 units were installed in Junkers Ju-88 night fighters. The war ended in May 1945 before the systems saw significant combat use. 3 years after capturing the Rotterdam Gerrit in February 1943, Germany had produced a system equivalent to technology. Britain had fielded operationally in 1942, and America had surpassed by 1943. The decade gap in radar physics was not metaphorical, it was literal. German centimetric radar in 1945 equaled British capability from early 1942, representing a 3-year lag in calendar time, but reflecting fundamental differences in technological approach and industrial capacity that translated to a decade's worth of development trajectory. The post-war assessment was unambiguous and backed by comprehensive documentation captured by Allied intelligence teams. Dr. Hachenberg, who had worked on the Rotterdam Gerrit project throughout the war, later became a distinguished radio astronomer and colleague of British scientists who had developed the cavity magnetron. After the war, Hachenberg worked at the Heinrich Hertz Institute from 1951 to 1961, became professor at Bonn University in 1962, and served as founding director of the Max Planck Institute for Radio Astronomy. From 1967 to 1978, playing a key role in planning the 100-meter Effelsberg radio telescope. In interviews conducted decades later, he acknowledged the magnitude of the German failure with professional honesty. In a 1973 interview, Hachenberg stated, "We knew the principles. Hollmann had patented cavity magnetron designs in 1935. We had the theoretical knowledge published in journals. What we lacked was the sustained commitment to develop theory into practice." The British made cavity magnetron development a priority and persisted through experimental failures until they achieved practical success. We calculated that success was unlikely based on our theoretical models and ceased trying. By the time we realized our error through examining the captured equipment, we were years behind and lacked resources to catch up. The gap was not in scientific knowledge, but in willingness to pursue development despite theoretical obstacles. Allied post-war intelligence teams documented the German radar programs systematically through multiple operations. The ALSOS mission, tasked with assessing German scientific capabilities in physics and electronics, conducted detailed investigations of German radar research facilities, interrogated scientists and engineers, and examined captured equipment and documentation. The Combined Intelligence Objectives Subcommittee sent teams to examine German industrial facilities and technical institutes. The British Intelligence Objectives Subcommittee conducted parallel investigations. The combined reports painted a detailed picture of German radar capabilities and limitations. The post-war assessments found German radar research sophisticated and effective in areas where Germany had invested consistently. Würzburg tracking radar represented excellent engineering within its frequency range. The conical scanning technique provided accuracy approaching theoretical limits for that wavelength. Mechanical construction was robust and reliable. Operational doctrine was well developed. Freya early warning systems were effective for their intended purpose, with good range and reliability. German radar-directed anti-aircraft fire was more effective than Allied equivalents using similar wavelength technology. Where Germany had pursued radar development consistently, results were respectable and sometimes superior to Allied equipment in comparable categories. But in centimetric wavelengths, German research had effectively stopped in 1940 to 1941. The ALSOS mission teams found German laboratories equipped with captured Allied radar equipment that was being studied when the war ended. German engineers were still analyzing technology the Allies had moved beyond, trying to understand 3-centimeter systems, while Allied development had progressed to even shorter wavelengths. The gap was not that German scientists were less capable intellectually. The gap was that German science had been working on different problems, while Allied science solved the critical challenge that defined the technological trajectory of radar development. The strategic implications were profound and measurable. Centimetric radar enabled Allied operations that would have been impossible with longer wavelength technology. The Battle of the Atlantic turned decisively in Allied favor in 1943, largely because coastal command aircraft using ASV Mark III could detect submarines that German boats could not evade. U-boats were forced to remain submerged more, reducing effectiveness and requiring battery charging in daytime when visual detection was possible. Strategic bombing became progressively more effective as H-2S and later 3-centimeter H-2X allowed accurate navigation and bombing through weather conditions that would have scattered earlier raids. Night bombing accuracy improved from miles to hundreds of meters. Allied night fighter capabilities decimated German bomber forces attempting attacks on Britain. RAF night fighters, equipped with centimetric AI, intercepted German bombers with efficiency that made strategic bombing of Britain too costly to sustain. By mid-1943, Luftwaffe bomber operations against Britain had effectively ceased. None of these advantages depended solely on radar, but in each case, centimetric radar provided capabilities that German forces could not counter effectively because Germany did not possess equivalent technology and could not develop defenses against capabilities they could not duplicate. The cavity magnetron represented a paradigmatic example of technological surprise in warfare. Germany understood the theoretical principles involved in magnetron operation. German scientists had worked on magnetron designs and had published research in international journals. Hollmann's 1935 patent demonstrated German researchers understood multi-cavity magnetron concepts. Yet when confronted with British achievement, German engineers had to admit they were years behind in translating theory into practical high-power devices. The surprise was not that cavity magnetrons worked in principle, which German physicists accepted. The surprise was that they could work at power levels and frequencies German calculations had deemed impractical for military applications. The British had not just built better equipment through superior engineering, they had demonstrated that German understanding of what was technically feasible was fundamentally incomplete. German theoretical models that predicted magnetrons would be unstable and low-powered at centimetric wavelengths were revealed as incorrect or based on incomplete understanding. British experimentalists had found solutions that German theoreticians had declared impossible. This represented a failure not just of engineering but of scientific methodology, showing the limits of purely theoretical approaches without extensive experimental validation. The industrial dimension of the technological surprise was equally significant and perhaps more strategically consequential. German engineers eventually learned how to build magnetrons approaching British performance. The LMS-10 magnetrons produced by Telefunken functioned comparably to British CV64 units they were copied from. German scientists understood the physics. German engineers could replicate the designs. But Germany could not match British and American production capacity. The tens of thousands of magnetrons produced by British and American industry dwarfed German production of hundreds over the entire war period. Allied magnetron production represented industrial mobilization for electronic warfare at scales. Germany never attempted and could not match given resource constraints and competing priorities. Radar tubes were being manufactured with the same industrial techniques and volume production methods used for artillery shells or aircraft engines. Quality control systems ensured consistent performance. Standardization allowed interchangeable components. Production volume transformed advanced technology, requiring specialized expertise into abundant commodity that could be deployed across all military services in numerous applications. German radar remained specialized equipment produced in limited quantities by skilled technicians. The decade gap in radar physics was not truly a decade in calendar time from British invention to German production capability. From British breakthrough in February 1940 to German limited production in April 1945 was approximately 5 calendar years. But in terms of technological capability, German radar in 1945 matched British capability from 1941 to 1942. This represented a 3-year lag in calendar development time, but reflected deeper issues in development trajectory and industrial capacity. During those 5 calendar years, British and American radar advanced through multiple generations of improvement. By 1945, British systems operated at 3 centimetre wavelengths with H2S Mark III, providing resolution, allowing detailed city mapping. AI Mark X airborne interception radar could distinguish individual buildings. American systems included APS-20 airborne early warning radar, with ranges exceeding 150 kilometers, and the capability to track numerous targets simultaneously. Ground mapping radar like H2X provided resolution showing individual streets and buildings. Gun-laying radars like SCR-584 could track aircraft automatically and direct anti-aircraft fire onto targets, invisible in darkness and weather with accuracy that made German flak systems seem primitive by comparison. German radar in 1945 was trying to match British capability from mid-war, while Allied radar had progressed far beyond. The human dimension of the story involved thousands of scientists and engineers on both sides, working with intelligence, dedication, and patriotism. German radar engineers were not incompetent. They were talented professionals with excellent theoretical training, working under increasingly impossible conditions. Trying to match technological achievements that required resources and infrastructure Germany no longer possessed by 1943 to 1944. British and American radar scientists were not superhuman geniuses. They were competent professionals who benefited from institutional decisions made years earlier to prioritize radar development and from industrial systems capable of translating laboratory success into production hardware at scale. The difference in outcomes reflected differences in strategic decisions about resource allocation made years before the war, differences in approaches to managing technology development, and differences in industrial capacity and organization. Britain made radar development a national priority in 1935, when the technology was immature and unproven. That early investment created expertise, infrastructure, and momentum that paid off when war came. Germany developed radar but treated it as one technology among many, important but not commanding the focused priority Britain gave it. When Germany recognized centimetric radar's importance in 1943, the gap was too large to close given limited time and resources. Otto Hachenberg's career illustrated the ironies of technological competition transcending warfare. During the war, he worked desperately to understand and copy British radar, analyzing equipment recovered from crashed aircraft, attending AGR meetings, contributing to German efforts to close the technological gap. After the war, he collaborated with British scientists, including some who had developed the cavity magnetron he had studied so intensely during the war. British and German scientists worked together using surplus Würzburg radars for radio astronomy research, tracking solar emissions and cosmic radio sources. The Würzburg radars that had been built to track Allied bombers became instruments for peaceful scientific research, mapping radio emissions from the Sun, Jupiter, and distant galaxies. Technology developed for destruction found beneficial application in fundamental science. Hachenberg worked alongside R.V. Jones, the British scientific intelligence officer who had orchestrated British understanding of German radar capabilities during the war and had helped plan deception operations against German radar. Former enemies became colleagues united by scientific interests that transcended wartime divisions. In the community of scientists, national hostilities gave way to shared pursuit of knowledge. The Rotterdam Gerät itself, that specific captured magnetron that revealed the technological gap to German scientists in February 1943, eventually made its way back to British hands after war's end. British intelligence teams recovering German radar equipment and documentation found German magnetron copies and examined how successfully Germany had replicated British technology. Technical analysis showed German copies were functionally equivalent to British originals, confirming German scientists had solved the reverse engineering challenge competently. The LMS-10 magnetrons worked properly, generated appropriate power, and operated at correct frequencies. German engineers had understood the technology and could manufacture working copies given sufficient resources and time. What they could not solve was the industrial-scale challenge of mass production under wartime conditions with limited materials and Allied bombing disruption. British magnetrons were being produced by thousands monthly in multiple factories. American production reached similar scales. German production peaked at perhaps 20 units monthly. The gap was not scientific knowledge but industrial capacity and the prioritization decisions that allocated capacity. Germany could build magnetrons. Germany could not build them in numbers that changed strategic equations. The lessons from the cavity magnetron technological surprise shaped post-war thinking about technological intelligence and research management in ways that influenced Cold War military technology development. Military establishments on both sides recognized that understanding adversary technological capabilities required more than monitoring what scientists published in journals or presented at conferences. Practical capability often diverged dramatically from theoretical knowledge available in open literature. An adversary might know scientific principles without being able to implement them effectively, or conversely might achieve practical success despite apparent theoretical limitations. Assessment of technological threats required understanding not just adversary science but industrial capacity, research infrastructure organization, strategic priorities reflected in resource allocation, and management approaches to technology development. The cavity magnetron surprise illustrated risks of mirror imaging, assuming adversary capabilities and limitations matched one's own. German engineers had calculated that high-power centimetric magnetrons were impractical. They assumed British engineers faced the same limitations and theoretical obstacles. This assumption was wrong, with strategic consequences. British experimentalists had found practical solutions that German theoreticians had declared unlikely to succeed. The cavity magnetron experience also illustrated the importance of experimental validation over pure theoretical analysis. German researchers had developed mathematical models predicting magnetron behavior at centimetric wavelengths. The models predicted instability and low power. Rather than conducting extensive experimental programs to validate or refine the models, German research accepted the theoretical predictions and focused on frequencies where theory predicted success. British researchers conducted extensive experimental programs, building numerous prototypes, testing variations, and eventually finding configurations that worked despite theoretical predictions of difficulty. This reflected different research cultures. German scientific tradition emphasized theoretical rigor and mathematical analysis. British tradition, particularly in engineering disciplines, emphasized experimental empiricism and practical demonstration. Neither approach was inherently superior, but in this specific case, the British experimental approach discovered solutions that German theoretical approach missed. The lesson was that theory and experiment must work together, with experimental results informing theoretical development and theory guiding experimental investigation. Modern historical analysis of the cavity magnetron gap places it among the decisive technological developments of World War II, comparable in strategic impact to radar itself, code-breaking capabilities, atomic weapons development, and proximity fuse technology. Each represented not just scientific achievement, but successful translation of science into practical military capability at industrial scale. The cavity, magnetrons. Significance was that it enabled a category of radar applications that longer wavelength technology could not match effectively. Without centimetric radar, many Allied tactical and strategic advantages would not have existed or would have been far less effective. With centimetric radar, Allied forces possessed capabilities. German forces could not effectively counter because Germany lacked equivalent technology and could not develop effective countermeasures without understanding the underlying principles through their own development. The decade gap was not merely historical curiosity or academic point. It was strategic fact that influenced military operations throughout the war's final years, contributing to Allied victory in measurable ways across multiple theaters and operational domains. 70 years later, the Rotterdam Device story remains a symbol of technological surprise, intelligence windfall, and strategic failure in technology development. That small copper cylinder, machined with extraordinary precision from solid copper blocks, represented years of British research, investment, industrial development, and engineering refinement that Germany had not matched. When German scientists examined it in February 1943, they held physical proof that their understanding of technical feasibility was incomplete. They had assumed limits that did not exist, while their opponents had achieved successes German theory deemed impossible or impractical. The gap was not merely technological, a simple matter of one side having better equipment. It was epistemological, representing a gap in understanding what was achievable and how to organize scientific and industrial resources to achieve it. German science was excellent by any objective measure, but it had been directed toward different priorities based on different assumptions about what was technically feasible and what was strategically important. By the time Germany recognized the significance of centimetric radar, the term technological and industrial gap was too large to close before war's end given Germany's deteriorating strategic situation. In February 1943, as Professor Leo Brandt examined that captured magnetron in the Telefunken laboratories in Berlin, he held evidence that Germany had lost a technological race they had not known they were running. British engineers had been working for 3 years on technology German scientists had dismissed as impractical, based on theoretical analysis. American industry was producing the devices by thousands monthly, while German industry struggled to build dozens. The path from laboratory curiosity to decisive military advantage had been followed successfully by the Allies, while Germany pursued other priorities based on different assessments of technical feasibility and strategic importance. By the time Germany recognized the significance of centimetric radar and attempted to close the gap, the technological distance was too large to overcome before war's end. The captured device was more than an intelligence windfall, providing insight into enemy capabilities. It was revelation of strategic failure in technology development that no amount of desperate effort could reverse given time and resource constraints. Germany's excellent scientists and engineers could understand the technology. They could not replicate the years of development, work, and industrial scale-up that had occurred while Germany was focused elsewhere. The cavity magnetron story illustrates that technological advantage in warfare comes not merely from having capable scientists, but from sustained institutional commitment to translating scientific knowledge into practical capability at industrial scale. Germany had the scientists and the theoretical knowledge. What Germany lacked was years of continuous development focused on this specific technology. The industrial infrastructure specifically tailored to electronics manufacturing at scale, and the strategic patience to pursue research that did not promise immediate tactical advantage. Britain and America had made different choices, investing in radar development as long-term strategic priority, beginning in mid-1930 seconds, when the technology was immature and unproven. They committed resources, built infrastructure, trained specialists, and persisted through failures and setbacks. By 1943, those investments had created insurmountable advantages in the most strategically significant electronic warfare technology. The decade gap was not accident or bad luck. It was the predictable outcome of different institutional decisions about how to mobilize science and industry for war. Decisions made years before the war began. Today, microwave ovens in millions of kitchens worldwide use cavity magnetron descendants, generating microwaves at power levels and frequencies that German scientists in 1943 believed impossible to achieve practically for military applications. The technology that decided electronic warfare battles in World War II has become mundane consumer appliance component, mass-produced in factories across Asia, costing mere dollars per unit. The physics that seemed so challenging that Germany abandoned serious pursuit has become undergraduate engineering curriculum, taught to students who learn in hours what took years to discover during wartime research. What appeared as extraordinary achievement in 1940, requiring cutting-edge physics and engineering, became routine industrial practice within decades as manufacturing techniques improved and economies of scale reduced costs. But in the specific historical context of World War II, That achievement represented crucial advantage that influenced strategic outcomes across multiple theatres of war. The small copper cylinder that Luftwaffe night fighters captured near Rotterdam in February 1943 was evidence that warfare had entered new technological domain, where theoretical understanding alone was insufficient for competitive advantage. Industrial capacity to manufacture advanced electronics at scale would be as important as armies in the field. Germany had fallen behind in ways that could not be rectified before war's conclusion, despite having excellent scientists and engineers who understood the principles once they examined the captured technology. That was the decade gap in radar physics, revealed when German scientists examined a British cavity magnetron and admitted, with professional integrity that transcended wartime propaganda, that they were years behind in technology that would help decide the war's outcome. The gap reflected not intellectual inferiority, but strategic choices about research priorities, resource allocation, and technology development approaches made years earlier, when consequences were not yet apparent, but would prove decisive when war came.